So to price corporate bonds, what we really need to use are risk-neutral probabilities of default. So let's see how we compute these probabilities. So these are called risk-neutral, or sometimes market-implied or measure Q probabilities of default, in the sense that these probabilities come from the market, from market prices. So let's see how we extract the probabilities from observed market prices. Let's start with a very simple example. Let's say a one-period zero-coupon bond. And if I observe the price of the bond, V0 here, I can represent that price as the discounted value of the expected payoff. Right? So with some probability, the bond will, with some probability, the bond will default. So if the bond defaults, I will get just the recovery value. And with the remaining probability, so one minus that probability, the bond will stay alive, so I'll get the full face value, so it will be this thing times 1, right? So this is the expected value. And then I'm going to discount the expected value at the risk-free rate, okay? So this is called risk-neutral pricing because it seems that I am discounting a value at the risk-free rate, which would be appropriate if investors were risk neutral, okay? But obviously investors are not risk neutral, so the name here, the risk neutral probability is a bit misleading in the sense that I am not assuming that investors are risk neutral. What I am doing is I am adjusting for the fact that investors are really risk averse by messing up the probabilities. So instead of calling these probabilities the usual P we have been using before, now we are calling them Q to denote that these are adjusted probabilities. They are compensating for the risk aversion that investors really have. So how do I compensate? Well, if I'm not putting the risk correction here in the denominator, I have to put the risk correction here in the numerator, and I do that by putting more weight in the bad state. So it is as if investors would see this event here as more likely. So the probability of default under the risk-neutral measure, this Q, is higher than the probability of default under the physical measure. Okay. All right, so let's see how we can estimate these probabilities from market prices. So let's start with the simplest possible case, which is just a one-period bond, right? So I can, if this is just a one-period bond, I can solve this equation that I have here. I observe the market price, I assume some recovery rate, I can observe the risk-free rate from the swap market, and I can solve the equation for Q, okay? So that's one alternative. The second alternative, which is sometimes more convenient, is to work with spreads. Okay, so instead of writing the bond price like this, I can write the same bond price in this spread-like fashion. So notice that what I'm changing now is that in the numerator I'm putting the best possible case, the best cash flow, which is the case of no default, where I get the face value. This is a zero coupon bond, so I just get 1. And I am adjusting for risk aversion in the usual way in the denominator by putting the risk-free rate plus some spread to compensate for risk. Okay, but what I have on the left-hand side, here and here, it's the same thing. It's the same market price that I observe in reality. So that means that the right-hand sides have to be equal as well. So that's what we have here. I'm equating the two right-hand sides of this side, this equation 5.4 and this equation 5.3. Okay. So solving this equation here for Q, I get this expression that you see here. All right. So a very quick example. Suppose I want to know what is the probability of default of the issuer of a zero coupon 1-year bond trading with a spread of 80 basis points. So that's that S. If the expected recovery rate is 40% and the risk-free rate is 5%. So basically just plug in the numbers in here and you get 126% for the probability of default. I have the solution here. This example 531. So this is the first risk-neutral pricing approach. This is the approach with the spread. I can solve for Q and I get the 126. Okay. Just a side remark before moving on, but that is very important for intuition. Let's say that interest rates are small, so this term here, the denominator is approximately 1. So I can write this whole thing by ignoring this part here as just this, right? Just ds and 1 minus r, which means that the spread, this term, is equal to q times 1 minus r, and 1 minus the recovery rate is what we call the loss given default. So basically what this is saying is the following: the spread that I charge on a bond is approximately equal to what? This is the loss that I expect to have. So this is the loss times the probability, so it's the expected loss, right? This is the expected loss. So this is saying that the extra amount that I charge to invest on a corporate bond, the spread, should be approximately sufficient to compensate me for what I expect to lose, okay? Plus a little bit more, because this is not what I really expect to lose, but it is adjusted for my risk aversion. So it is a little bit higher than my expected loss because I don't take risks for free. I am not risk neutral. I am really risk averse. So the spread compensates me for what I really expect to lose, plus a little bit more for taking risk. So the risk neutral expected loss. Okay, so now let's see how to compute the probabilities of default for periods after 1. So extend this to any number of periods. Okay, so I can start with a set of bonds, and from that I can get the corresponding zero coupon rates by one of these methods we have seen before, like bootstrap, Nelson-Siegel, and so on. Okay. So I'll denote S by S the spread between that risky rate and the risk-free rate for the corresponding maturity, right? So basically what I'm going to do is just a natural extension of the previous equation that we had up here for, this is for one period. So if I am going to do this for more periods, I'm just going to discount for more periods. And that's exactly what we have here. This is the way to get the probability of default for any period t, which basically is just different from the previous equation by the fact that I have here now a discount factor for t periods on both sides of the equation, right? So it's easier to see this with an example. Suppose that we have these two periods that we have here. I have the risk-free rate flat at 4%, and then I'm going to try to get the probabilities of default for a bond that has this rating A, okay? And I have the rates for these 2 years at 6 and 6.1, and the spread would be the difference between 6 and 4 to 6.1 and 4, 2.1, okay? And I will assume a recovery rate of 40%, okay? And again, what I want to do is I want to find the probabilities of default for the first year and for the second year, okay? Let me show you this. So you have all the details here, but even in more detail, it's here, okay? So the first year is exactly the same as we did before, same equation. I want to find Q, and I get 3.14%. For the 2-year period, I can extend the equation for 2 periods. So I'm discounting for 2 periods using the appropriate rates, right? The risk-free rate is flat at 4%, but the risky rate is not flat. So it was 6 for 1 year, 6.1 for 2 years. Okay, and I get Q of 6.53%. So now I have to be careful that what comes out of this equation is this Q02. So it's the total probability between now and 2 years. It's the total probability of default over this 2-year period, okay? What I also want to know is what is the marginal probability of default. So representing what we have so far in this tree, we are alive at time 0. 1 year from now, we will be in default with this probability of 3.14% that we got from here, okay? And then 1 more year, we can survive our default. We will be in default at some point in these 2 years with this probability of 6.53% that we get here. But now I can also compute this marginal probability, which is just the probability of defaulting between 1 and 2, okay? So how do I get this? Well, I know that the probability of default at any point between 0 and 2, this number here, is equal to 1 minus the probability of surviving, which is this top branch here, right? So using this notation, Q02 is equal to 1 minus the probability of the top branch, which is 1 minus Q01, 1 minus q, 1, 2, right? This top range here. So replacing by the numbers we have, 653, 3.14, which is this one here, and leaves me just this unknown that I need. And that turns out to be this number, okay? So that's this probability here. Okay. There are some sites that show you these probabilities. This is one example. The only point I want to make here is the following. So if you look at this, you have a bunch of probabilities. So you have here, these are probabilities for different years from 1 to 20, the marginal probabilities of defaulting over these years, okay? But what is interesting to note here is that this is computed for a recovery rate of 0. Then if you went to the site, you would see another table below this one for a recovery rate of 0.1, and then another table for the recovery rate of 0.2, 0.3, 0.4, and so on. So you'd see a bunch of tables, each one for a different assumption about the recovery rate. Okay, so this is just to stress that the recovery rate is something that we have to input. We have to specify what it is. And this is just the probabilities of default for this specific group, BAA2 industrial. So you would see another set of tables for other set of firms, for other rating categories. Okay. Okay, so at this point we have two different probabilities. Let's compare them. We have the risk neutral and we have the objective probability. So the one we are talking about now, the risk neutral probabilities, are used for pricing bonds and for pricing credit derivatives, as we will see later on. The previous probabilities we have talked before, the objective probabilities that you get, for example, from the logit model that you estimated, or from transition matrices and so on, those are used for managing credit risk. Okay. It is interesting to compare them, okay? So we know that the risk neutral probabilities Q have to be larger than the objective physical probabilities P, okay? But the point is, by how much should they be larger than P, okay? If you actually look at the dates, at the data, you'll see that they are not just larger, they are much more, they are much bigger than what we should expect. So they tend to be higher by a factor of 2 to 3. Okay. So so what does that imply? If you recall this idea that we had that related the probabilities to the expected loss, what we are saying is that the spreads we observe in the market are too large relative to the losses that we expect, and even accounting for reasonable degrees of risk aversion. So in other words, what we are saying is that it seems that when you look at the data, it seems that the credit spreads are too good to be true, are too large. They are compensating investors for more than the risk that would be reasonable to be compensated for. Okay, this is sometimes called the credit spread puzzle, right? If you look, there is a paper that does this comparison. What you see here in this figure is the following. So you have, for different rating categories, you have these bars. The left-hand bar, this gray one, shows the spread you observe in the market for AAA, AA, and so on. The rightmost bar, so this one here, and this one here, and so on, shows you the spread that you should be observing for a reasonable level of risk aversion and for the losses that you typically observe. Okay, and the point is that what you actually get in the market is higher, much higher than what you should be observing. Right? And that's particularly true for this more safe bond, for these safer bonds. All right. So we can discuss different arguments against this, against calling this a puzzle. There may be other factors at play, like liquidity, and there may be other factors at play, like events that were not included in the sample of this paper, like, for example, the 2008 crisis. And it would be interesting to see what happens after the current crisis we are in now, and for sure there will be a lot of defaults, and maybe the spreads turn out to be not as good as they look once you account for these events where you actually lose a lot of money. Okay.